Good afternoon, Professor Alderady. My name is Joshua Casalvera.
I'm Hector Perez.
My name is Nicholas Hallstrom.
And this is our presentation on Flexure strain measurement. So, for our objectives, we measured load and deflections in the beam bending. We analyzed the relationship between load, bending stress, and strain, and we gained a general understanding of how strain gauges attach to specimens and just how to measure voltages corresponding to strain overall. For some context, flexure testing is a fundamental field in material science, and it's used to evaluate stiffness, strength, and elasticity in beams. It allows us to connect theoretical mechanics like Hooke's law and moment of inertia to actual real-world applications. And just learning multiple ways to generate and understand strain allows engineers to make more efficient and safer structures overall where bending is prevalent. For our results, we created a load displacement graph for the tested beam, created a stress strain curve for it as well, and the displacement position graph of the deformed beam. And we also created a table representing Young's modulus related to stress and strain, and with a reference value that we have referenced later on. For our materials, we used the regular acrylic beam with the strain gauge attached to it, the wires for electrical connection that were attached to the actual machine, the tape and adhesive to connect the strain gauge to the actual acrylic, the test machine for load and displacement, the multimeter for voltage check, and the force gauge for displacement as well, the foam mold for actually bending the acrylic, and a conditioner amplifier for reading the strain gauge output. For the setup, we placed the acrylic beam on two supports directly underneath the force attachment thing, and we turned it around so that the strain gauge wouldn't be crushed by the thing. And we attached the wires to the actual machine with the screws, and the dial and force gauges were 0. For the actual procedure, we applied the load and we measured and recorded the strain gauge using the multimeter, not going past 10 pounds. And we attached the wires from the strain gauge to the multimeter, and from there we attached it to the conditioner amplifier as well. And we pressed the acrylic beam against the foam mold to create the voltage output, and then we calculated strain from there and then compared it to the actual theoretical strain and got a percentage error from there. For our controlled variables, it was most things in this experiment. It was a testing machine, the support span length, the actual dimensions and material of the acrylic beam, as well as the strain gauge and positioning. And really the only manipulated variable that we found was the actual applied load and overall displacement of the material, of the acrylic.
So this is our data collection right here. So we have 3 separate graphs. This one's the load versus displacement, and what this shows is a positive linear relationship, because as you increase load, the more it flexes, the more the displacement increases. This is our micro strain graph right here, and it shows another positive relationship. And then this is our displacement versus position graph, which shows the bell graph relation. And then this is our Young's module beam original, and then this is the Young's module using the stress and strain. And then this is actual from our mind. And what we gathered from this is that using the original version is giving us a 37.2% error compared to the stress and strain that only gave us a 7.2%. And what we can gather from this is that the stress and strain method gives us a more accurate value than the original Young's modulus.
For discussion here, the result in summary analysis. We did 2 different methods to find the Young's modulus. One was displacement, and the second one was stress strain gauge. For the displacement, we got 2.01 gigapascals, and for the stress strain, we got 2.97 gigapascals. The strain-based Young's modulus is 48% higher, and the reported percent error versus reference was 3.91%. Real-world implications. We can confirm these values using. Confirm these usefulness of local versus global measurements for design and inspection. This can highlight how measurement technique and geometry control affect material qualification.
So to conclude, our Young's moduli went from about 2 gigapascals to 3 gigapascals, with the strain-based modulus being around 48% higher. The overall percentage error in comparison to the reference was about 4%, which indicates good agreement overall. The discrepancies likely came from strain gauge bonding issues, thickness measurement error, and just general machine compliance. Our main takeaway from this was that our results demonstrated how measurement method and setup precision influence evaluation and real-world design liability.
For future work and recommendations, for some lab fixes, we could bond or replace any suspect gauge, measure thickness with a micrometer at several points and use the mean for better accuracy. We could expand tests as well in order to see how much they vary. And for instrumentation upgrades, we could use a temperature compensated bridge to reduce temperature effects.
And thank you for listening to our presentation. Have a good night.